All right, this video is on specific heat capacity. In it, we are going to do some calculations as well as define what heat capacity is. Okay, so our lesson objective, okay, you're going to be able to use data to determine heat transfer using specific heat capacity. So we'll get to what specific heat capacity is here in a second. We'll do a little review. Okay, temperature is the measure of average kinetic energy of the molecules or atoms in a sample. Okay, so the higher the temperature, the greater the kinetic energy. The lower the temperature, the lower the kinetic energy. Okay, the higher it is, the faster the molecules are moving or atoms are moving, and the lower the temperature, the slower they are moving. Heat is transfer. Heat transfer of thermal energy. So transfer of energy from one body or one entity to another, or one system to another. Okay, heat is always going to flow from high temperature to lower temperatures. Okay, very important point. We cannot measure the amount of heat. All we can do is look at the change that occurs, or I can see the change in heat. So I may not be able to see how much heat something has, but if I change it, or I change the amount of heat and I measure that, then I know how much heat it had, and I know how much heat it'll have, or pretty much know the temperature where it is and then where it was, and by looking at those change in temperatures, I can find out what the change of heat is. The formula that we're going to use is MC delta T, which is, this is delta H. This means heat. Okay, delta, a little triangle, delta means change. So I'm really looking at the change of heat, because remember, I said right here, I can only measure the change in the heat. Okay, change in heat is equal to the mass times the specific heat capacity. Now, the specific heat capacity is a value that is unique to each individual species. You will not need to know what the heat capacity is for every species or for every substance, but there is one that you will know by the time it's all said and done, and that is the specific heat capacity of liquid water. And that is equal to 4.184 joules per gram times degrees Celsius. Okay, you'll know that one. We're going to use it a lot. Okay, and then lastly, delta T, which is change in temperature, which is, got cut off right here, temperature final minus the temperature initial, meaning I'm going to have a change in heat. I want to know what the temperature is before that transfer and after that transfer. If I know what it is before, that is my TI, and if I know what it is after, that is my TF. Okay? So, what is so important about heat capacity? Let's go ahead and take a look at the difference between, say, this pool and the side of the pool, or the brick. Okay? The smaller the number, okay, gram degrees Celsius, the smaller the number, the less energy it takes to raise 1 gram of that substance by 1 degree Celsius. Okay, so if I have a really, really low number, what that means is it's not going to take much energy to cause something to heat up by a degree. Okay, versus if I have a higher specific heat capacity like water, okay, it takes more energy to heat it up. Okay, perfect example between this brick and the pool. If the pool had very low heat capacity, or a specific heat capacity, then on a hot day, water would boil. Okay, but the fact that it takes so much energy to raise a gram of water by 1 degree Celsius, that's why pools are wonderful, because they have such a high heat capacity. They can all that water can absorb so much heat, and it won't raise the temperature of the water. While the brick is very hot, as you know, when you get out of the pool. Okay? So, examples. How much energy is needed to raise the temperature of 10, which I'm going to change to 10.0 grams of water from 10.0 degrees Celsius to 20.0 degrees Celsius. Okay? Now, this is a really important skill that you're going to need to find, is when you notice that there's a change in temperature, you know it's going to be MC delta T, because this is the only equation that we have that has a change in temperature that we're going to be dealing with. Okay? So when you see a change in temperature, you know you need to use this equation. So what does this mean? This means I want to know how much energy, and the unit of energy is joules. I want to know how many energy units of joules are going to be needed to raise 10 grams, so 10.0 grams of water from 20 degrees Celsius, or 10 degrees Celsius to 20 degrees Celsius. The reason why I wrote it like that is because, remember, it is TF minus TI. So, writing out the whole equation, I'm going to go delta H, which is J, right? So, I'm going to go ahead and say J joules is equal to grams times specific heat capacity, which is joules per gram degree Celsius, times degree Celsius, right? Times change in temperature, which is in degrees Celsius. It's very important that you have all of your units be the same. Because if I'm solving for, say in this case, I'm solving for energy. That means over on this side, I need to cancel out everything that is not joules. How I have it set up right now, right? This is really grams over 1. This is really degrees Celsius over 1. Well, look, I can cancel out my degrees Celsius. I can cancel out my grams. I'm left with joules, which is what I'm trying to solve for. Okay, so let's go ahead and do the problem so you guys can see it. Okay, so delta H equals MC delta T, which is equal to 10.0 grams times the specific heat capacity is 4.184 joules per gram degrees Celsius. Remember, this is the specific heat capacity of liquid water. It is a value that you need to know, and you will use a lot. Okay, and my change in temperature, which is going to be 20.0 degrees Celsius minus 10.0 degrees Celsius. Yes, I want you to write that out. Okay, so when I rewrite this again, 10.0 grams times 4.184 joules per gram degrees Celsius times 10.0 degrees Celsius. Okay, so take a look at my units. My grams cancel out. My degrees Celsius cancels out. Should have canceled out. Why aren't we canceling out? And let's see. Okay, there we go. Canceling out. And then I just do my math, which would be pretty much 4.184 times 100, which would be 4184.4 joules, which is delta H. Is that my correct answer? No. Why? Because my answer right now has 4 sig figs, but my answer needs to have 3 because that 10.0, either 10.0, only has 3 sig figs. Okay? And obviously the product of with 3 sig figs versus 4 sig figs, my final answer needs to be in 3. So 418 joules is my final answer. Okay? So what does that mean? That means it takes 418 joules of energy to raise 10 grams of water 10 degrees Celsius. Okay? So, let's take a look at the next one. I have 1,000, exactly 1,000 grams sample of water that gained 33.5 kilojoules of heat. What is the change in temperature? So now even though I don't have a change in temperature listed, I'm solving for change in temperature, which means I'm going to use delta H equals MC delta T. Okay? What kind of information do I have here? Well, I have a mass. I have an energy value. I have my delta H value right here. Okay? And I have the heat capacity. I have C because it's water. I know what is 4.184 joules per gram degree Celsius. Now, it's important that I wrote that, or I said that, because it's 4.184 joules per gram degree Celsius. Well, that's not joules, that's kilojoules. So I have to do a quick dimensional analysis before we get started. Okay? You don't need to show me the dimensional analysis. I just need you to do it. Okay? 3.5 kilojoules over 1. Okay? And then I'm going to have 1 kilojoule is equal to 1,000 joules. Sig figs, remember this conversion factor right here does not play a part in sig figs. So my final answer here is 33,500 joules. Okay? Which I'm going to take that value Okay, 33,500 joules equals MC delta T, mass, which is 1,000 grams, times 4.184 joules per gram degrees Celsius times change in temperature, which will be in degrees Celsius. So I'm going to multiply these two numbers right here together, the 1,000 and the 4.184. So I'll end up with 33500 joules equals 4184. Okay, joules. Now, thing is, when I multiply these two things together, my grams canceled out. So now all I'm at is joules per degree Celsius times delta T. Okay, I didn't divide over here. On both sides, I divide by 4.1. Oh, sorry, not 4 point. Excuse me. But 4.184 joules per degree Celsius. Right? I divide that by both sides. My final answer is going to be in degrees Celsius because I just canceled out my joules unit. Delta T is going to equal, if I do my sig figs, with 8.01 degrees Celsius. And that's it. Okay? If it's pretty simple, folks. If I give you, there's 4 variables there. I'm going to give you 3 of them. You got to solve for the other ones. Okay? Now, there can be an instance where I may say solve for the initial temperature, solve for the final temperature. It's the same process. It's just you need to realize that when I do that, I'm not solving for the change in temperature. I'm solving for one of the components, either the final or the initial. Okay?